Hi, good evening, everyone. So welcome to this edition of Robotics Café. We have Dhananjay from MathWorks, who will be giving a talk on from simulation to sky, developing autonomous UAVs with MATLAB. So Dhananjay is a senior software engineer at MathWorks. He is a member of Autonomous Aerial Systems Group. Prior to joining MathWorks, he has worked as a image processing engineer at Urmi Systems Private Limited in Hyderabad, where he worked on autonomous landing of UAV project. And Dhananjay received his PhD from aerospace engineering and master's from electrical engineering, also from IISc. Okay, currently, he's working on developing tools in MATLAB/Simulink for autonomous UAV applications. Something that is not there in bio. He's a avid math guy. He worked on a lot of guidance systems. So, with that very small introduction, Dhananjay, it's over to you.
Yeah, thanks, Sujit. Thanks for the nice introduction. Uh, Before starting, I would like to thank you and your colleagues for inviting me to give this presentation in this Robotics Cafe forum. So to begin with, so in the recent past, we have seen the use of UAVs mostly in warfare, which is unfortunate since their main applications were civilian. So leaving that aside, let me start my presentation. So I'm Dhananjay, as Sujit mentioned, working in MathWorks in the Aerial Vehicle Systems Group. So this is the title of my presentation, Developing Autonomous UAVs with MATLAB. So the agenda for today's presentation is first I'll just discuss about why we need UAVs, what are the motivations, what are the challenges in developing a UAV system. Then I'll spend quite some time on the UAV toolbox, the features, the capabilities that it provides to the users. Then I will show a few workflows, basically some demos about the use of UAV toolbox for developing autonomous applications. Then we'll dive into how to use Simulink integration and the code generation. This is basically used for more realistic simulations like software in the loop, hardware in the loop, and deploying it to real hardware systems. Then finally, I close the loop by going into flight log analysis. So after a flight is done, we get a lot of data. So how do we use the data and what it can be used for? So this is the agenda for the presentation. And also previously we had Dr. Tanvi Prakash, where she gave a good perspective of the UV applications in industry. My talk will be more focused towards academic and research demos, but with some applications in industry. So why UAVs? So as we all know, even from the previous presentation, UAVs are used in applications like delivery and logistics, where last mile is the problem. We have UAVs in infrastructure inspections, like inspecting power lines, windmills, and wind turbines. Then we have UAVs used for precision agriculture, field mapping, crop health. Also, some of the other applications are search and rescue, and also, of course, in defense and security. So if you want to group the UAV applications, we can group them according to the consumers, like where we have nowadays we have a lot of drone shows where formation flight is important. Then we have UAVs being used for photography, filmography. Then we have commercial applications like mining, construction site inspections, delivery, and of course defense like surveillance, combat. So these are some of the important application areas of UAVs. So the basic challenge that we want to address is how do we develop, validate, and deploy UAV algorithms safely, efficiently, and even quickly. So we want to make sure that we can rapidly prototype the algorithms and be able to deploy it onto real hardware. So this is the challenge that we want to discuss. So just to, before diving into the presentation, I'm assuming that everyone is aware of MATLAB, or at least have used MATLAB Simulink in some form. So MATLAB is basically a programming environment, numerical computing environment. It's used to analyze data in terms of matrices. We can analyze log data. We can develop algorithms using scripts, functions. We can visualize, plot the results. Whereas Simulink is more of a block diagram environment where we can model your plant dynamics, controllers, simulate the system, and generate code and deploy it into embedded hardware systems. So with that, so coming to the challenge, how do we go from simulation to real flight? So the first stage is developing your algorithm. So the user picks an algorithm, chooses some of the tools available, and develops his algorithm. Next stage is he needs an environment to simulate his scenario. Like we have some scenes like Unreal Engine or a simple low fidelity models where he can create a scenario quickly. Then we need to test the algorithms in real hardware. So we need some connectivity and deployment interfaces. Finally, once everything is done, we have to do some analysis on the flight log data. So this is the basic development cycle that one follows when developing a UAV application. So just giving you an idea of the UAV toolbox, what it enables you. It enables you to develop flight controllers. It enables you to model your plant. We support different types of vehicles like multirotor, fixed wing, VTOL, which is nothing but vertical and takeoff and landing vehicle. And also we can connect to some external ground stations like Q ground control and mission plan. Also, since we want to do some realistic simulation and deploy to hardware, we have support for deploying your algorithm, like the flight control algorithm, onto PIXOC hardware. You can also deploy your plant model on SpeedGoat for some real-time simulation. And then if you have some complex computations, we can deploy the algorithm onto NVIDIA Jetson or Raspberry Pi to do some autonomy algorithms like obstacle avoidance. So now I'll just dive into the UAV toolbox, like how it is structured and grouped. So we have basically the 5 sections in the UAV toolbox. One is for developing algorithms. Then we have 2 scenario generator tools. One is the cuboid scenario simulator, where we can create low fidelity environment simulations. We have the Unreal engine for photorealistic simulations. Then we have the connectivity and deployment blocks, where we support PX4 and ArduPilot hardware. And finally, we have the flight log analysis app to analyze all your flight log data. Okay, so if anybody has seen Simulink, like if they open the UAV toolbox library, so this is what appears on the screen. Like we have 4 groups: algorithm, simulation 3D, utilities, MAVLink, and UAV scenario. So I'll just go through each of these groups just to see what are the things available in the toolbox. So first is the algorithm, simulation, utilities, MAVLink, and UAV scenario. So in the algorithm section, we have simple models first, guidance models. We call it as guidance models for multicopter and fixed wing. Then we have simple line following, path following algorithms like orbit follower, waypoint follower. Then we have trajectory generation tools, like we can generate min jerk and min snap trajectories, which are useful for multi-rotor UAVs. And also there's a built-in obstacle avoidance algorithm if you want to use it in your application. And then we have this simulation 3D support, where we can create scenes in Unreal. This for more realistic simulations. We support a sensor suite of LiDAR, camera, and ultrasonic sensors. So this is for more realistic simulations. This particular scenario can be used. Then if you want a low fidelity environment, we have the UAV sensor modeling and scenario. Here also we have support for INS, GPS, and LiDAR. So this is for quick prototyping. So this particular scenario simulator is used for quick prototyping of your algorithms. Yeah. So this is what I mentioned about the cuboid scenario. So we can create approximate buildings using cubes, and then we can also simulate sensor data using like GPS, INS, LiDAR sensors. Then we have the capability to study the effect of winds and gusts on the particular performance of UAV. And next is like we need some way to communicate with the hardware or the external peripherals. So MAVLink is used in this. So basically MAVLink is nothing but a lightweight messaging protocol, which is used to communicate between drones or between GCS and the drone. So the data is exchanged between the different components in the UAV using MAVLink. So once, and there are certain utilities like coordinate transformations, which will be helpful in developing your algorithms. Then finally, like we want to deploy what are the algorithms we have developed into real hardware. So we provide support for 2 types of hardware boards, like one is the PX4 and the other one is ArduPilot. So these are the 2 hardware boards which we support. Yeah. So let me just show one of the demos. So I'll explain along the way. Yeah. So this is a demo, shows like the UAV safe landing. So what happens here is that the idea is like the UAV first takes off. It is designed to follow a particular trajectory. So during the execution of the mission, suppose the UAV encounters some emergency. So what should it do? So now what we have done is we have equipped the multirotor with a LiDAR sensor. So once the emergency is triggered, it uses the LiDAR data, that is the LiDAR point cloud data, to create a map of the surrounding environment. So it uses that data, and then using the map, it tries to find a safe landing zone. So here we can see like the what a map created by using the LiDAR data. So it searches this particular map to find a flat area which is suitable for landing. So once that is detected, the UAV uses its control algorithm to go and directly land at the correct location. So I can just speed it up a little. Yeah.
So Dhananjay, how does it find its safe landing spot? Is there any metric?
Yeah, that's in the algorithm. So I don't want to go into too much, but some of the metric is like how the roughness of the terrain or the slope of the terrain. So all that is inbuilt in the LiDAR processing. So yeah. Yeah. So yeah, basically, yeah, once it finds, then it it safely lands in that location. So this, yeah, I'll just go into the details like how it's implemented. Yeah, so this is the model. This is entirely in simulation. So we have built it in Simulink. So this has the following modules, like we have the quadcopter plant. So this we have used a low fidelity model, since the idea is to test the algorithm, like the landing side detection algorithm. And we have a simple PID controller. The main thing is the state flow diagram here, state flow graph. So here it decides when the UAV has to change modes, like from mission mode to searching and landing zone detection. So this is done in the state flow. Okay. So now, so that was for a simple landing area. The other example that I want to demonstrate is like how you can simulate the UAV landing on a moving ship. So the ideas are similar. So here we have the UAV moving over the ocean, like, and there's a ship, and there's a small area marked for the UAV to land. So the idea is that the UAV has to detect that landing zone and then safely land in that region. So again, we use the LiDAR sensor data for detecting the landing zone. Yeah. So yeah, so in both of the examples that I showed, I'll just go through like how the planning is done. So first, we have the plant dynamics, so which we need to model both the multirotor as well as the ship's dynamics. Then we have the perception control algorithm. Then we have an environment where we want to simulate the UAV. Okay, so for the plant dynamics, so we have two plants, like the ship as well as the multirotor. So we can use 6 equations of motion for modeling the plant. If you are just testing the algorithm, we can go with a low fidelity model. Yeah. So what are the things that are modeled in the plant? So we have the forces, like we can model the gravity, aerodynamic forces, and the propulsion systems. Then we can model environmental effects like gravity, atmosphere, magnetic field. And yeah, as I mentioned, 6 equations of motion can be used to model the plant. Yeah, if we want to, based on the application, we can replace this with a low fidelity model. Next comes the ship. So here they just model this ship's rolling action and the forward motion. We can also model some of the ocean current effects for the movement of the ship. Yeah, so this is the entire workflow. So we have the perception algorithm, which tries to find the landing point. Then we have the planning and decision module, which tries to find the trajectory which it needs to take to find on the landing point. Then we have the controller, which actuates the motor and tries to follow the desired trajectory. So this is the entire workflow to do this landing operation. Yeah. So yeah, those were examples of multirotors. Now I just want to show about a VTOL UAV. So VTOL is nothing but a vertical takeoff and landing UAV, which has the capability to work in both multirotor as well as a fixed wing mode. So the UAV that I am considering is a tilt rotor VTOL UAV, where the front two motors are able to rotate. So in the forward flight, that is the fixed wing flight, both the motors point forward, and when it's in multi-rotor mode, all the rotors are pointing upwards. So we can model this again using the 6 equations of motion. The main thing is about the force and moments that act on this VTOL. So to model that, we have different blocks. Like one block models the aerodynamic forces which affects the UAV. Then we have the propulsion system, basically how the tilting action affect the propulsion. And then we have some environmental effect like gravity. And also we have the ability to simulate like wind, model the wind. Okay. Yeah. So the control structure is slightly more involved than just a multi-copter or a fixed wing controller. So here we have two controllers like multi-copter controller, fixed wing controller, and depending on the flight mode in which it is moving, we switch between either one of them. Also, the main concern is how do we schedule the tilting of the rotor. So how do we switch from multi-copter controller to the fixed wing controller? So there are two transitions that happen. That is the forward transition when the UAV transitions from a copter to fixed wing mode, and the other back transition when the UAV transitions from forward flight, that is the fixed wing mode, to multi-copter mode. Yeah, so yeah, here is another demo. Yeah, so we have designed a certain path that the UAV has to follow, and then everything is designed in Simulink. So yeah, this is just to test our algorithm, so how it's able to work. So we can see that the UAV follows the particular path. So we have some animation showing how the tilt rotors are working, and then yeah, we have the Unreal simulator showing the VTOL. So yeah, and finally it can land. Yeah. Okay. Yeah, so that was basically everything was done in the simulation environment. So everything was done in Simulink. So, but now we need to go into more realistic simulations. So for that, we have something called the SITL, software in the loop, and hardware in the loop workflows. So for this, we use two popular software like AutoPilot firmwares are the PX4 and ArduPilot. So they support a wide variety of airframes like multicopters, fixed wing, VTOL, submarines, rovers, boats. They have strong interface with external simulators, like we can connect to JMavSync, Gazebo, Unreal Engine. And also, this is one of the common choices in research and some of the industrial applications. So these support rapid prototyping, and then we can also test our algorithms in real hardware using these two autopilots. So just there's some confusion regarding what is PIXOC and what is PX4. So just to clarify that is PIXOC is the physical hardware. So here I'm showing a PIXOC 4 board, and PX4 and ArduPilot are the software programs that run on this hardware. So basically the software programs are the brain of this particular hardware system. Yeah. So what is software in the loop? So software in the loop is runs the autopilot firmware in your computer. So we don't still run it in the real hardware. We run it in our host computer. Then Simulink controller. So basically what we do is we replace the autopilot firmware, that the controller that is there in the autopilot, with our controller. So suppose we develop a controller in Simulink, we replace the autopilot's controller with our controller. And so that enables us to test our algorithm on a somewhat more realistic environment. So, and then finally, we need to validate how this particular workflow works. Okay. So this is the workflow. Like we have the controller model. We deploy it onto the SITL autopilot firmware. Then we connect it to a simulated vehicle. Again, here, as I mentioned, we are not using a real vehicle. We use a simulated vehicle. So we exchange data between the simulated vehicle and the SITL firmware. And also we can connect to some ground station just to log some data or plan some mission. So this is the workflow for how we do SITL. Yeah, so here, so in order to do this, so we have like, we have developed a controller, like we have the position and attitude control for quadcopter in Simulink. So this controller will replace the controller that is existing in ArduPilot or PX4, so whichever board we choose. And then we have the plant model. So both we design it in Simulink. Okay, so let me show like how this particular simulation works. Yeah, so first we run the controller. So the controller is running in the in your computer, host computer. Then we can load a mission file in. There are two mission planners like mission planner as well as QGround control. So I just given a basic simple triangular path for the UAV to follow. Yeah. So we can see that the data will be exchanged between the controllers, both which are developed in Simulink, and then yeah, here we can see like okay, so the UAV takes off and it follows the desired waypoint. So, okay. Yeah, so now the next level of realism is like we want to deploy your controller on a hardware. So HITL is what does that one. So we deploy our controller onto a real hardware, that is the PX4 board or the ArduPilot. Then what happens is that the autopilot computes the actuator commands according to the controller that you have designed. It sends it to Simulink. The Simulink sends the updated states to the controller, and that's how the loop is closed. So benefit is that we have real time, not real time, but real testing, and we don't have to fly actually. So we are still using the simulator, but only thing is we have deployed the controller on a real hardware. So some of the supported hardware is like we have Cube Orange Plus, PixOx series, and also Speedcoat and Jetson for some real-time target applications. Yeah, so this is a basic block diagram representation of what is happening. So we have the PixOx board, we have the plant dynamics in Simulink. So the communication is established between the PixOx and the Simulink model. We deploy the flight controller developed in Simulink to the autopilot. So this is just slightly one level more realistic than SITL. Okay, so finally, once we have done all the design testing in SITL and pure simulation, we want to fly and test it on a real quadcopter. So here we use the Holybro QAV 250 kit. So it comes with the PixOx 6C mini flight controller and a lot of sensors like GPS and IMU. So since we are in the office, so we had to set up this small cage. Like we don't have too much room to do real flight tests outdoors. So this is an indoor environment. We built a cage and then we just tried basic hovering and path following experiment. So it takes up to about 1 meter, then it does a small yawing motion, and then it comes back and lands. So the landing is not smooth, like it now just drops at the end. So depending on some threshold, we just stop the motors. So this another one, like this was more for educational point of view. Like we have the Parrot mini drone. So the students are given the task of controlling, designing the controllers, and then deploying their controllers on the small mini drone. So here we're just showcasing the line following algorithm here. So all this initial development was done in Simulink, simulation, and then real flight test. Yeah. So finally, it just hovers on this target location. Yeah. So the workflow involved is like, so as I mentioned, first is to do in simulation. So we have all the modules like the perception and guidance module, the flight management unit, the UAV dynamics, and the visualization. So all is in simulation. Next, once we go to real deployment, so we have the perception and guidance module on a Raspberry Pi. So it computes the algorithm for tracking the line, that's the red color path which you saw. When we deploy our controller on the PixOx 6C mini, and then we use the QAV quadcopter to fly the mission. Okay, so that was the indoor flight, but since we don't have the like option to fly outdoors, this one of the user stories that was it's available online, like by a team from NASA Langley. So they use this workflow, whatever I mentioned, to develop test their new control algorithm. So this is an outdoor flight where they did some maneuvers and were able to quickly prototype their algorithm and fly it in real. So once all this thing is done, so we get a lot of data from the flight. So if we use the ArduPilot autopilot, we have the flight log stored as bin files, PX4 stores it as ulog files. We need to do some analysis from the data and see how our UAV was able to perform. So for this, we have the flight log analyzer app. So we can download the flight log data from the UAV, upload it here, and log all the signals. We can plot all the signals, whatever the signals that are of interest, like how the tracking performance of the controller was, what was the health of the vehicle, and if there is a crash, we can use all this data to analyze that. So yeah, also the other thing what can be done is using the flight logs, we can do a system identification. So we can use it to identify aerodynamic parameters, some wind turbulence model, and also improve the fidelity of our plant. So these are all the workflows that is possible from the flight log that is collected during the flight. Suppose we have a test rig where something like this gimbal setting where the UAV is able to roll pitch. We can use this flight log data to test your controller performance. So this is one of the setup actually we have it. So this is used for controller tuning. So finally, the workflow is like the first is the design phase, where we select the airframe like the multirotor or fixed wing. Then we design a simple logic for path following. Then we validate that in simple scenarios like the UAV scenario or a more realistic visualization using Unreal. Then we deploy it in PX4 or ArduPilot, whatever the firmware you select. Once that is done, we collect the log data, analyze how the flight went, then use it for system identification, improve your model, and then do the whole cycle again. Okay. I just wanted to tell about, like, we have something called as the MathWorks mini drone competition, where we introduce the students to model-based design, like using Simulink models. We ask these students to design their algorithm for this Parrot mini drone. This is used because it's very safe and not dangerous to fly. The teams are invited to deploy their algorithms and test it. So it is some sort of a competition for to create interest in students. So here we have the workflow, like they design, they simulate in the simulation environment, then finally they deploy it on the real drone. Okay, so it's not required. Yeah, so I think to conclude, what I can say, like the MATLAB UAV Toolbox provides a complete layered workflow from dynamics modeling to real hardware deployment. We can design everything in Simulink, then deploy it seamlessly onto the PX4 and ArduPilot software. Then we cover different types of vehicles like fixed wing, multirotor, and even VTOL. We have code generation, that is, we can generate code and deploy it onto the embedded software. Finally, we have tools to do log analysis, which will be useful for system identification and improving your model further. So I think with that, that's the end of my presentation. Maybe I just took 10 minutes quickly, but yeah, thanks.
Yeah, and thank you all for attending, and have a nice evening. Bye.
Yeah, thanks.